All right, very good evening, everyone. Thanks for coming to the No Jargon Talk series, session 4. We have two wonderful speakers today, Christine Mazzola Deher and Lisong Chen. I'm gonna quickly introduce our first speaker, Christine Mazzola. She graduated from Mississippi State University with a degree in physics and minor in math. And she's about to be a sixth year grad student at Pitt in physics with her research focus in astrophysics. She grew up around science and have always been interested in astronomy. She has done a lot of mentoring for the department and have helped supervise an undergraduate research project and advised on graduate research work. She now spends most of her time procrastinating on writing papers or figuring out what her adorable puppy Sasha is stealing from the trash can. Very cute. Before I hand it over to you, Christine, for your talk today, I'm just gonna make it like a brief announcement. If you guys have any questions, this talk is going to last for about 5 to 10 minutes, maybe 15 minutes. And after that, we are going to have a question and answer session. We are going to use this very cool app, Slido. You can just post your questions anonymously there, and I'll just convey the questions to this Zoom meeting here, and Christine will try her best to answer those questions. Always feel free to unmute yourself and use the emoji of raise hand to ask any questions here right away. If you don't want it to be anonymous, feel free to do that. Um, and I'll just share the link for that Slido app here in the chat box. And over to you now, Christine.
All right, thanks, Yasha. I am going to, I can't screen share. You're gonna need to enable it.
So sorry about that. You should be good to do that now.
Okay, here we go. All right, can you see my screen?
Yep.
Okay, let me get into presentation mode. Okay, are we all good, Yasha?
Yep, that's
all right, perfect. So then I will get started. I'm gonna hide my participants view. Yasha, just bug me if anyone has a raised hand because I may not notice it immediately. And again, I'm happy to field questions during the talk. Don't feel bad at all if you're curious and want to ask something. Won't interrupt my flow at all. Okay, so today I'd like to talk about the research I've been doing for the past 5 years or so, scary as that is to say, studying twin star systems, much like the one in this iconic photograph from episode 4 of Star Wars. And I'm going to summarize the talk with the name Chasing the Double Sunsets, because there's lots of information to learn and there's still lots of unanswered questions. It's a really interesting growing field that will hopefully be even more interesting and well-researched going forward into the LSST era. So the rest of this talk I'm going to pose as questions that we're going to seek to answer and maybe leave a little unanswered. The first question I'd like to pose is perhaps the most important for any scientific presentation, which is just to get us all on the same page. Oh, and by the way, sorry, you may hear my puppy in the background. She likes to whine and she might scratch at the door a little. But anyway, with that out of the way, let's start with, scrolled ahead too far. The first question for any scientific talk, which is, what are we talking about? In this case, what is a binary star system? Let's start by going to the all-knowing Wikipedia. Their article on binary star systems first sentence reads, a binary star is a star system consisting of two stars orbiting around their common barycenter. So by binary, we obviously understand that to mean two stars, double stars, or twin stars, a variety of ways to refer to them. And by common barycenter, all we mean is what's illustrated nicely by these little movies taken from the Wikipedia article. Hopefully Zoom displays these okay. You can look up the article afterwards if they're not displaying well on the screen. Never know about these sorts of things. But presuming they're showing okay, hopefully you can make out the red cross in each of these little movies. That is the common barycenter for the system. And we see that in each image, the objects are moving around that common barycenter a little differently. So the movie on the left shows two stars that are of very similar masses, orbiting in what appears to be about a perfect circle around that common center point. When the two masses are very different, however, the motion looks very different as well. For a system that has a difference in mass similar to the Earth and the Sun, we see that the much larger object, here akin to the Sun, is basically right on top of that red cross, the common barycenter, and it's just wobbling around that central point. The much smaller mass appears to be orbiting the larger body, but in fact, it's orbiting that common barycenter that just happens to be located inside the much larger object. Now, the orbits need not be perfect circles. In fact, they can come in the form of a more generalized circle known as an ellipse, which is just an elongated circle here in this case. We see that when two similar masses are traveling in elliptical orbits, as in the movie on the right, the motion of the two stars is actually a bit different, which is why it's relevant to sort of separate out these cases. So binary stars come in all sorts of different shapes and configurations. Let's take a look at what some binaries look like as examples. And we're going to start with binaries that are shown in the media. The image on the left is taken from the Star Wars Rebels series, and we can see that the two stars are basically faint and fuzzy points of light that are different sizes and different brightnesses. And we can see that there's something in the bottom left corner that's a nearer object, probably a planet that we're seeing the stars off in the distance from. Now, the stars need not be out visible in space. They can also be visible from the surface of a planet, as shown both in Star Wars quite often from Tatooine's perspective, but also here in this image on the right, taken from Star Trek Deep Space Nine. So we can see sunsets on Earth are beautiful. Why couldn't double sunsets on alien planets also be beautiful? Which is why I think these sorts of star systems crop up quite frequently in science fiction, actually, because I think they're very photogenic. And I think a lot of people in science fiction do too. Okay, so now that we've seen two different, well, actually three when you include Tatooine, three different portrayals of binaries in media, what do binaries in real life in the wild look like as observed from Earth? So the image on the left was taken with the WISE survey, infrared survey, and the central part of the image is just basically a bright source. We can't make out any details from the image. It all just looks very bright and fuzzy. But when we look at that central region with a different telescope, the Gemini telescope in Chile, we actually see a very different picture. We're able to make out two different light sources here. They look like two fuzzy points of light. One is slightly brighter than the other. Looks like the one on the left is slightly larger, slightly brighter. So actually our portrayal from Star Wars Rebels is actually pretty accurate. It looks like something that we might observe in the galaxy. So that's cool. Now, these two stars are not that different in size, brightness, or mass, but that need not be the case. Binaries, like I said earlier, come in all sorts of different flavors. So the image on the right is Sirius A, which is the brightest star in our night sky visually. So it's very visible with the naked eye. In fact, it can even be visible in the daytime under the right conditions. That's how bright it is.
Yeah. Sorry to interrupt you, Christine. I think we are still stuck on the very first slide of your talk.
Oh no.
So sorry. I should have realized it before, and I was like, you're still talking about the same picture here. We still see the three pictures of similar masses, Earth, Sun masses, and similar masses elliptical orbit.
Okay, so it hung up on that image or that slide. I kind of wondered if it would. Let me try restarting the slideshow from where I had been. Okay, sorry about that, guys.
Yeah, no problem. Technical difficulties happen all the time.
And Zoom is extra unpredictable with these sorts of things, unfortunately.
Yeah.
Okay, do you now see my screen?
It still says it's starting screen sharing.
Oh no, Zoom has done this to me before. Okay.
Okay, now we can see.
You can see it?
Yeah, you just have to do the full screen.
Yes. Okay, do you see the images now?
Yep, now we can see that.
Okay, so sorry about that. All right, so you see the image on the left was the one I was talking about earlier from Star Wars Rebels. We have two different size, different brightness points of light that are kind of fuzzy. And the image on the right is the beautiful sunset that I was referring to. Okay, so Yasha, let me know if the slide advances okay.
Yeah. Now I can see
Okay.
the next slide.
Okay, I have a feeling those movies sort of messed up Zoom. I wondered if they would. But anyway, the image on the left here looks actually pretty similar to the one from the Star Wars Rebels series. Two fuzzy points of light that are of similar size and brightness, but slightly different, not significantly different. Image on the right is Sirius A and Sirius B, where the central star, Sirius A, brightest star in our sky, and it overexposed this image actually. It's so bright. And if you look in the bottom left corner, right underneath the cross, you'll see a dim point of light. That's actually a separate star, another companion that is orbiting this much brighter star. It's termed Sirius B. And it's actually the remnants of an old star that has already gone through its evolutionary period. It's sort of in the graveyard of stars, you could consider it. And that's why it's so small and so faint relative to the central star, Sirius A. So binary stars come in all sorts of shapes and sizes. We observe many of them throughout the Milky Way. And sort of what I would pose as the answer to this question, what is a binary star system? One sense is a really cool desktop background picture. They are very photogenic, which is why you often see them showing up in sci-fi. I think another reason they also show up so often in sci-fi is that they add an alien atmosphere to the planets that these series are trying to portray, because adding a additional sun to the sky automatically makes the planet look foreign to us. Okay, so besides how cool they look, do they have any scientific value? Is there any reason why astronomers should care about binary stars? So binary stars are actually quite common in the Milky Way. For sun-like stars, 2 out of every 3 stars that are sort of the same mass, the same temperature as the sun, are going to actually be in binaries. So they're really quite common. But beyond how common they are, I think there's an even better answer to this question. Astronomers should absolutely care about binary stars because binary stars are actually related to just about every area of astrophysics. So to illustrate this, the National Academy of Science runs the decadal surveys of astronomy, where scientists put forth white papers where they summarize the history of a subfield of astronomy, star formation, for instance, or galaxy formation, dark matter, etc. They summarize the history of the field, the current state of the field, and then where they think the field will be going in the future, and more importantly, what facilities, what telescopes would be needed to propel the field, and what forms of data. For instance, can we get existing data from current telescopes? We just haven't had the money or the time on those telescopes to get the data that we need, for instance. The survey summarizes all that information and prioritizes different research initiatives. So say this telescope would be able to provide data for all these different fields of astronomy. So putting our money there would benefit a lot of different people. It provides priorities. And that is actually used to advise the US government's funding priorities for the coming decade of astronomy. So the white paper on stellar multiplicity took a look at how binaries are related to most areas of astronomy you could think of. And it turns out you can check just about every box shown here in all these thematic areas. And a lot of these areas are very different from one another. We have the evolution of galaxies, how galaxies change over time. Of course, we have how stars form and how they evolve, but we also have how planets form and the planetary systems that result. and might be interesting as we start looking for planet B for future planets. Multi-messenger astronomy and astrophysics is also related to stellar multiplicity and stellar binaries. The talks we heard last week at the No Jargon series, gravitational waves and neutrino astrophysics, are both related to stellar binaries, as well as cosmology, the study of how the universe began and how it's anticipated to evolve and end. That too, in fact, is related to our understanding of stellar binaries. So I think the question, should astronomers care about binary stars, is met with a resounding absolutely. They all should be aware of binary star science because it's going to impact them in one way or another. Now, I don't have enough time to talk about all these areas, already running a little over time given the technical difficulties earlier. So I just want to briefly cover the two areas that my research has touched on. But of course, if you have questions about any of these thematic areas and how they're related to stellar multiplicity, please don't hesitate to ask after the talk or email me at any point. I'd be more than happy to have a chat about that. So the first field I'd like to briefly glance at is star formation. What can binaries tell us about how stars form? So spoiler, the answer is that trends we see with chemistry actually give us insight into the formation mechanisms of stars. So first, we're going to take a look at the observed trends that we see, and then I'm going to review the theory of star formation very briefly, just in a nutshell, so that you have the information you need to be able to interpret the trends that we see. So first, stellar chemistry has been determined through a variety of studies and methods to be negatively correlated to the close binary fraction. So what does that mean? It means that stars that have lots of chemicals, lots of metals, anything other than hydrogen and helium, those stars are far less likely to be in a binary. So we see here for iron, the more iron you have, the lower close binary fraction you have, the fewer systems are in binaries. For iron, it looks relatively linear. It's fit reasonably well by a line, right? Now, is this true for different elements? With the data that we have, we can start to answer this question. And this was something I looked at in my previous paper. So we looked at, for instance, two different elements shown here, magnesium and silicon. Turns out they're both also negatively correlated with the close binary fraction. We see a general downward trend, but the trends themselves are pretty unique. They are different. Magnesium does not appear to be well fit by a line across the entire region. At the very left side of the plot, it's not fit by a line well at all. Silicon is off doing its own thing. It's hook-shaped. It's completely different than the trends we see for iron and magnesium. All of this hints at the fact that there might be more complex interactions and processes going on that depend on the chemical we're talking about. That said, let's do a brief overview of star formation theory so that we can get to some interpretations of these results. So the first thing you're going to need in order to produce a star is a giant cloud of cold hydrogen gas, which is relatively abundant in the galaxy. They're not too hard to come by. You have some sort of shock that causes fragments or clumps to form within the gas cloud. Those clumps are going to be able to pull in more mass to themselves through gravity, attractive force of gravity. And those clumps are going to grow and grow until finally you arrive at these central cores that are surrounded by spinning disks of material. And just a neat fact, we think that planets probably form in these disks. So eventually, whenever these cores develop enough mass, they have gotten big enough, they disperse the disk, kind of complicated process here. We're massively oversimplifying, but eventually the cores also themselves have gotten enough material that they grow very dense and very hot, and they're able to push the hydrogen that they have inside them so close together that they can actually fuse and combine to form helium. And it's at that point that we would sort of say we have an official star that's been born. Everything before that is a protostar. but we now at this point have given birth to a brand new fledgling star. So how do binaries play into this picture? There's two formation mechanisms I'd like to highlight. The first is that nearby fragments individually form stars, but those stars are close enough together to become gravitationally bound. These stars are going to start out far away from each other, so they're going to form wide binaries, what we would call wide binary star systems, just because the stars began further apart, right? Now, the disk themselves, while they can fragment to form planets, well, if you gather enough material, heck, you've created a star, not a planet. So you can have stars that form inside these disks, and at that point, we would consider those close binaries just because these disks are much smaller than the scales of the cloud. So we're going to have two different mechanisms here, one for wide binaries and one for close binaries, obviously massively oversimplified here. With that in mind, we can look at how our understanding of chemistry impacts the formation of these binaries. So the first thing to note, and this is coming from models, is that for elements like iron, magnesium, and silicon, everything that we've studied, the less you have of those elements, the more likely the gas is to fragment, which means you're more likely to have binaries. The more individual fragments you have, more likely you are to have these binary star systems. Now, there's sort of a different effect that can go on, which we saw evidence for in silicon, which is that when you have lots of a certain chemical, it turns out that the gas is able to cool more effectively, which means that more material is able to fall into it. And it ends up being able to fragment more easily too. It becomes very fragile. And that is going to also result in more binaries, which sort of explains the hook-like shape we saw with silicon. But this is only true for certain chemicals. So a lot more research needs to be done to fully understand these effects. Okay, now we're already running long in this talk. So I just want to very briefly go through the other aspects of my research, which is what can binaries tell us about stellar evolution? So the summary for this is that binaries tend to spin fast and die young. We see evidence for impacts on stellar rotation and potential stellar engulfment that occurs in these binaries. So we're going to do the opposite of what we did in the previous topic, which is go over sort of the theory of stellar evolution, and then we're going to relate that to the results that we see with close binaries. So first, let's talk about what's going to happen to the sun. This is a plot of the effective temperature of the sun and its radius, its physical size. So as a star like the sun ages, its radius changes pretty dramatically. The green part of the line shows what happens whenever the sun is very young in that sort of protostar stage. It's going to accumulate more mass and is actually going to grow more dense and more dense. Its temperature is going to increase until it reaches its temperature and size of its adult life. And it's going to spend the vast majority of its life in the yellow phase of this curve. And it's very stable. Even though that's the vast majority of its lifetime, it doesn't change very much in its physical size and temperature, which is pretty great if you're trying to live on a planet around that star. You don't want the star changing too much in physical size or temperature in order to have life. But eventually, our sun, like any other star, is going to start running out of fuel. Your car runs out of fuel, it's not going to move. Sun runs out of fuel, all sorts of interesting things start to happen at the center. When it becomes elderly and cranky, it's actually going to increase in its physical size. And this is a log scale plot. The dotted line at the bottom shows the current radius of our sun. The dotted line at the top shows what we expect the sun to grow to, which is 200 times its current size. And let me tell you, you can say goodbye to Mercury and Venus whenever that happens. And you're going to have a bad time on Earth if you're around whenever the sun grows to that size. So even if humanity survives the next couple centuries, we're going to have bigger problems that we're going to have to solve in the next coming billion years or so. So what does this mean for close binaries? If it's bad for planets, maybe it's also bad for binaries. Turns out that we see strong evidence for this in our data. For very close binaries, the size of the stars matters a heckin' lot. So this is a complicated plot, but I'm going to try to break it down into a couple interesting regions. So the y-axis is roughly related to the radius of the star. Stars at the top half of the plot are small, physically small. Stars at the bottom half of the plot are huge. They're very large. When we look at the plot from the left to the right, the x-axis, the shaded region, are stars that are very unlikely to be in close binaries. Not impossible, just less likely to be in close binaries. The stars that are in the unshaded region are very likely to be in close binaries by contrast. In fact, some of them are more or less guaranteed to be in close binaries. It's really the only reasonable explanation for their behavior at that point. So when we look at the two different regions, we see that stars that have small radius are, as it turns out, much friendlier to having nearby companions. Just like the sun being at a smaller radius means we get to keep Mercury and Venus, you're going to tend to be able to keep closer star companions as well. Now, once you get to the large radius, well, a lot of these stars have probably already evicted their neighbors. They just could not survive that hostile environment of the star starting to encroach on their territory.
Sorry to Christine. So what's the x-axis here in this plot?
So in astronomy talk, it's the effective gravity, the log g of the star, which is roughly, or sorry, did you say the x-axis or the y-axis?
The x-axis.
Okay, sorry, the x-axis.
Yeah, I can see the radius on the y-axis, but yeah. I'm kind of confused for the x-axis.
So the x-axis is, again, in astronomy speak, the change in the radial velocity of the star. So it's the Doppler shift. How blue or red is the light that's coming to us whenever the star is moving towards or away from us.
Gotcha.
This is an indicator of how fast it's moving. The faster it's moving, the more likely it is to be moved by a close companion. Otherwise, why would it be changing speed so much?
Sounds good. And also, like, I would like to give you a time warning, so we just have 3 to 4 more minutes for you.
I have one more slide.
Perfect.
Right. Sorry, I know this was running pretty long.
No problem at all.
So the final thing I'd like to point out is the color bar on this plot. So just like the Earth and the Moon tug on each other and cause tides in our oceans, close binaries can also tug on each other. In their case, it causes their rotation speeds, their days, to become much shorter. Their rotation speeds get much faster. And that's what's plotted on the color bar here. So when we look at the top corner of our plot, which are stars with small radius and very likely to have binary companions, we notice that overwhelmingly they tend to have very high rotation speeds. They tend to be yellow and light green colored stars, which is indicative of these tidal effects that's going on. So that's my upcoming paper. Like Yasha said, talk's already running long. So thank you for your attention, and please feel free to ask me any questions. Thanks, everybody.
Awesome. Very amazing, Christine. Very interesting. Loved it.
Thank you.
I would like to open the ramp for any quick questions for Christine. Feel free to just raise your hand or just unmute yourself.
Were there any questions on Slido?
Yeah, I do one question. So the question is, can we actually see stellar binaries in other galaxies, especially far, far away ones? I know resolving stars is almost impossible for them.
Okay, so that's a really awesome question, actually. So long story short, University of Pittsburgh and CMU, several of the faculty members have a joint NSF grant where we're studying stellar multiplicity. I am using that grant to mainly study binaries in the Milky Way, but a student at CMU is studying binaries that are in dwarf galaxies, the galaxies that are much smaller that orbit our Milky Way. you can't really see the two stars individually like we could in some of the photos at the beginning of my talk. Let me see if I can go back to those. Like the person asking said, it's very difficult to resolve those stars, right? But this technique that I was sort of explaining to Yasha of using the Doppler shifts, the change in the speed of the star, even if you can't see both stars, you can still see evidence for the presence of a second star. So you can see binaries in that way in external galaxies, at least the ones that are close enough to be able to actually see individual stars. And the cool thing is that by checking to see if there are binaries in those dwarf galaxies, people are able to get a better handle on the actual orbital speed of those stars in the galaxies themselves, which is important for estimating the amount of dark matter in those galaxies. So you really see what I mean about you need to know about binaries to study things like dark matter, something you would think is not at all related to binary stars. So that's what Rachel is doing over at CMU. Her advisor is Matt Walker. So very cool stuff. Yes, you can observe some binaries in external galaxies and do cool things.
Very well explained. That totally makes sense. Yeah, I would like to thank you again, Christine. Zoom round of applause for you for an excellent talk. Without further ado, I would like to post this link for feedback. Please take a couple of minutes to fill this for our speakers, to give them feedback about how their talk was. It would be really helpful for them. And I would like to introduce our next speaker now, Lisong Chen. He's a fourth-year graduate student. He's from Sichuan, Chengdu. He's working with Iris Freitas on elementary particle physics and cosmoparticle physics. His other interests include ethnomusicology, anthropology, and history. Very cool, Lisong. So happy to have you here today. Over to you now.
Me too. Let me try to share my slides first. Can everybody see my screen now?
We can see the screen, but you just have to enter full screen mode, I think. Yep. Looks great.
Okay, it advances, right?
Yeah.
Okay. Okay. Let me first just thank the organizers for indulging me giving the very off the rail talk about archaeology instead of physics. But since I'm not an expert on the subject anyway, I guess it fits the theme, no jargon talk very well. So my original topic is said to be given a brief history of the Sanxingdui, the Three Star Mound civilization. However, I found it would be more interesting to just take a look at this this civilization through a very special angle that one can embed this embed the information I give into a bigger picture about the history of human being. So before I get into Sanxingdui civilization, I'd better give a short introduction about the early civilization in East Asia. So basically, despite a lot of facts, some kind of factions from politics and so forth, the major civilization stem from the midstream and downstream of the Yellow River Valley, known as the Sha and Shang, located here. It's this is a Beijing, as one can imagine. So it's quite close to the Central Plains. And this is where the people thought the birthplace of the Chinese civilization, ancient Chinese civilization. And all the Orthodox Chinese dynasties stem from there. And well, before it formed up into this way, it went through a integration process, which integrates all these scattered smaller cultures around the Central Plains. And the traditional narrative tells us that after integration, this system of so-called mandate of heaven in ancient in ancient China is well established, and it started developing the writing system, the bureaucracy, and stuff like that. Well, as one can see that this kind of integration pretty much took thousands of years to finish. As one can see that there are lots of cultures scattered around the entire map, including Yangshao, Longshan, and also the Mazzola from the very west part of the China. Actually, Mazzola, people found the first bronze object at this site. So we would believe that the bronze technique, the metallurgy came from the West. However, this narrative got challenged by the excavation that happened in 1986 in Sichuan, Guanghan, Sanxingdui, as the arrow pointed here. Actually, it's also the place of my hometown, where an exotic, exquisite, and also hauntingly beautiful ancient civilization revealed itself there. So geographically, one can see it locates at the edge of Tibet Plateau, and it's also surrounded by all kinds of mountains. So Tibet also obviously lots of high mountains on the west, and on the north side it's the Qing Mountains that block the way from this basin all the way to this one, where the Xi'an located, also turned out to be the major capital city in Chinese history. And also on the east, this is another part of mountains that block the way from this basin all the way to the east. So it's pretty much a blocked out area, but in such an area, a very prosperous and a very advanced bronze civilization has been found. So we believe this civilization existed around 1700 BC all the way to 1150 BC. And it's actually a part of the successive civilization or a kingdom called Shu. And it features such extremely unique culture in regard to the rituals, customs, and innovations. And the people have found lots of very bizarre things there. For instance, they found the shells from Indian Ocean. One can see here is Sanxingdui in this little square, and the Indian Ocean is all the way to the lower left corner. And from this square to the Indian Ocean, you have to climb over Himalaya mountains or some secret forest in the river, like nobody knows. So it's pretty weird. And we also find ivory. Back when elephants, they weren't there in the first place. And sophisticated metallurgy technique and all the bronze objects found at this site are very, very bizarre compared to the other bronze object they found in midstream and downstream in Yellow River. And there's no reliable recording history whatsoever. So it's really, really mystic. So to just give you a bit of flavor, let's just jump right into those cute, bizarre masks, which is also made this civilization famous for. So these are the bronze masks, gilded with gold, like this. And such kind of gold gilding requires very advanced technique in terms of like gold beating and the leafing, all kinds of that. I will talk about it later. And these are some very some masks that shows the very unique feature that they all tend to exaggerate the protruding eyes out of the these masks. One can see that they exaggerate the shape of eyes like this, and which cannot be found anywhere else. And this is one of the largest masks people found in the spiritual sacrificial pit. And one can see that they punched holes at the top of the mask, seem to be a place to hang the entire mask upon somewhere during the ritual. So people would believe this is some object that used in some kind of a sacrificial ritual. And it's huge. It's definitely not used for not to use practically. So all these kind of masks, just makes people think about some connection to the aliens. There's a very popular conspiracy theory about whether it could be a alien civilization or not. Also, you can find some popular culture that related to it. This is some Ultraman anime from Japan, and people found they all feature some same eye shape. They all have this protruding eyes. But really, the people in Sanxingdui, they are really into eyes. They almost had this kind of eyes mania. So in this picture, it's all those bronze eyes found in the sacrificial pit of Sanxingdui. And it has some underlying reason of that, because remember, it's the entire district is so-called, the city-state is so-called Shu. The kingdom Shu has a Chinese character shows on the left-hand side. One can see that there are lots of variations of that, but all of them feature an eye at the top of the character, right? One can see that. And even in the modern Chinese, it still means eye if you just turn it like 90 degree counterclockwise, it still means eye. And all these kind of characters just keep reminds us some other kind of famous eye, like Horu's eyes from Egyptian civilization. And it's kind of similar in terms of the shape to the Chinese character to some extent. So that gives us some kind bit of like it opens up a door of like imagining some kind of connection between the Far East and the Near East civilizations. So another object found in the sacrificial pit of the at the Sanxingdui is the gold scepter. It turns out to be actually just a golden foil like this. It's 1.42 meter length and 500 gram. And one astonishing fact is only within like 0.02 centimeters, almost as thin as a piece of paper. And such kind of thin golden foil requires very, very high technique in terms of gold gilding. So this kind of like a precious object also needs the very fine gold beating and smelting techniques of the time. So one can see that this is actually a carving from Egyptian civilization. See, people, they have to melt the metal, either the gold or something else, and then they will interleave a piece of gold inside of a skin, like a sheep skin, goat skin, or like an intestine, like an ox intestine, and then use the hammer to beat it. One must beat it uniformly and precisely, so to have a very uniform golden foil coming out. And they even had a carving on top of it. So imagine having this such exquisite carving on a sheet of paper. And all these patterns seem to be very, very metaphoric. But one can obviously see that this is kind of like a fish, this is a bird, and this is like a human figure. People would suggest this could be a priest, and but we have no idea what those animals mean. And we also see an arrow that crossed through both the bird and the fish. It probably means some kind of sovereignty and power, the kingship. So, but everything over there is still very mysterious, that we have any concrete idea to interpret it. But one thing that we noticed about is that it is so strange comparing to other bronze civilization in the east side of the continent, because in the traditional narrative, we believe the Central Plain civilizations must feature some kind of symbol. It's called ding. It's kind of bronze vessel. The ding is a symbol of power and divinity, and also the sovereignty of the so-called Son of Heaven. And in traditional narrative, people also believe that the entire ancient China is divided by 9 states. Each state will share a vessel, and only the men or women who mandated by the heaven will be able to use all these vessels altogether. So this is a very strong evidence point towards the establishment of the vessel symbol in ancient bronze civilization in China. But it has nothing to do with what we found in the Sanxingdui, where it is a scepter used for showing the sovereignty, power, and divinity. But we can easily find similar things in West Asia. For instance, we can see all the kinds of like the figure of scepter in sculpture at the top of Kola Hammurabi, and there are lots of very famous scepters in Egyptian culture, like the was or the semekhe. They almost become like a very popular icon. And there's another carving from the ancient Farsi, where the Darius is grabbing a scepter, shows the sovereignty of the emperor in Persia. So with all that aside, there's another interesting object called sacred tree found in the sacrificial pit of the Sanxingdui. It's very, very tall. It's a 4-meter height. I still remember the first time I went to the museum, I have to walk through a long, dark corridor to get to see this tree, and a just very astoundingly beautiful when it shows up in front of my eyes. Uh, this tree has 9 bronze birds standing on branches. Um, at the beginning, when the archaeologists found it in the at the sacrificial pit, it has been scattered into hundreds of pieces, and it took them almost 10 years to put them together, and it's still not perfect yet. Like they're still missing the top, and we believe there is a 10th bird standing at the top. Why is that? Why do we believe there should be another bird at the top? Well, it's just because we have we have a corresponding literature that describing some very similar thing, and this kind of description shows up in the literature. Also, share some common things with other literature that we found in West Asia. So let me just get into that. The bird, the snake, and the tree. So for this sacred tree, we find birds at the branches. We also find the dragon, but more likely to be a snake underneath. So in the ancient Chinese classic literature, there's one book called Classic of Mountains and Seas, which is supposed to be some kind of a, we thought it was just a book with full of fantasy, like 40 years ago. But then we found Sanxingdui. We excavated Sanxingdui, and everything starts making sense, because in this book, it says there's a tree from the east called Fu, in which the sun rises. A tree from the east, I'm sorry, this should be west, called Ro, in which the sun sets. A tree at the center called Jian, connecting the heaven and the earth. And the sun is carried on the back of the bird called Wu, which should be a crow of the sun. And there used to be 10 sounds. So like kind of like a denary system in astronomy. So one sun is on the top, at the top of the tree, and the other 9 are underneath. And this is matched with the tree perfectly. 1 on the top, 9 underneath. So we would suspect that there will be another bird at the top of the tree, because each bird corresponds to 1 sun. And there's a snake at the bottom called Rushe, and it eats wood. And if you have taken any kind of world civilization class in undergrad, it might sound familiar to you, because the Epic of Etana, which is a emperor in Sumerian, there's also very, very similar myth like that about the tree and the bird and snake. So it says in the beginning, an eagle and the serpent inhabit a tall popular tree, and the eagle nesting at the branches, and the serpent is at the root. There's a man one day came by, and the eagle and the snake, they keep fighting with each other to keep some kind of a balance of the world. And one day this man came by, and the bird told him, if you would like to help, I can carry you on all the way upon the heaven, and let you talk to all those gods at the heaven, and let you become an emperor of the world. And so this is basically a story of the Etana. Etana, the emperor shows up in the ancient history in Sumeria, and which found out to be the the one who had been sovereign the entire kingdom for over 1,500 years. Obviously, it's a myth, but it's just the story itself shows lots of similarities from the ancient classics of China of ancient China. And the one pay attention that this book came out around 457 BC, but the Epic of Etana is way much earlier. It's 3,000 years BC. And there's another very famous tree in Gilgamesh. It's also published around the 3000 BC, and this tree is called a hulub tree. And it also described in the Gilgamesh that the serpent and also the birds called Anzu inhabit on the tree. Also, there are some other life of tree symbols found in other civilizations on the continent. So it just everything they share some kind of similarities, like under the tree is some kind of symbols that shows the animals or the creatures about the underwater, the underground stuff, and something at the branches is about the flying objects, animals, or some kind of celestial figures. And the third object I would like to introduce is this some kind of weird wheel that you don't know what it is at the beginning if you take a look, because it looks like a steering wheel, it looks like a chariot wheel, and people will also guess is a shield ornament, or maybe it could be just a prank made by some farmer live close by. They just threw some kind of random thing inside of the pit and let other archaeologists to find out. But it has some similar things from the West Asia. People find similar bronze object about a sun in Anatolia. It's supposed to be a bronze object that belongs to heat. And also they found some similar pattern representing the sun in the ancient Egypt carving. And there's another side things that, so the this kind of is it called insect in ancient Egypt carving is very, very similar to what we found in Sanxingdui. There's a bronze insect here. So is it just a coincidence, or they do have some correlation? Well, we know that in the old continent, we would think the all those kind of bronze civilizations, they somehow develop themselves individually, and there's no much of influence from one to another because of the geographical distance. And you see the Sanxingdui is located between the Indian Valley civilization and the midstream, downstream Yellow River civilizations. And it kind of linked both civilizations together, because we found the shells from Indian Ocean, we found ivory, and it also definitely shares some common things with the Yellow River civilization. And also from previous objects I introduced, you can obviously see there's some similarity to share with the other civilizations that around the Middle East, Egypt, and the Mesopotamia. So, inspired by cosmology, cosmology could be some kind of archaeology to some extent. Now we have this beautiful plot about CMB background. that when we take a look at this picture, we see the the temperature is so uniform that we just can't help but think of there must be a moment that those photons interact with each other sufficiently, so they can share the same features afterwards when they scatter, when they get expanded, right? And you can take this kind of inspiration back to the real archaeology. So in terms of the diffusion of metallurgy technique, that one can see that the darker the region is, the earlier time they get into the Bronze Age. And the green side is the copper ore. The black spots is the tin, and the red is for the gold ore. And one can see that it's supposed to the spreading of the technology for making bronze object is spreading out, starting from for instance, the one can see the around the region of Black Sea, where people also thought to be the starting point of the Proto-Indo-European. They have lots of copper ore, so it's straightforward to let us think that they might develop the bronze metallurgy technique very early, and then they spread out later on. So if we map this to an entire continent, we could imagine, for instance, people around the Black Sea region, they spread out their technique through the Grand Steppe in Central Asia all the way to the East Asia, and there are some of them spread out and going to the East Turkestan. They go through the corridor called Hexizoulang, and then getting to the midstream, downstream Yellow River, and one of the branch they went into the Sichuan basin and merged with the local people in Sanxingdui. And some other, you can also imagine the connection between other two civilizations. For instance, they can go through the bay and the ocean, cross with each other. So it really shows a map about the earliest globalization, or in other way around, the diffusion of the technique. That one can imagine the globalization happened way earlier than we can imagine. It starts at the Bronze Age, where the early human being, they carried the advanced technique in terms of stories, in terms of math, in terms of technologies of making bronze object, iron object, so on and so forth, and they spread out over the entire continent. And then maybe once they develop the shipping on the sea, they can use the sea to start in the spreading, which makes sense why in this area at Shu, the kingdom where we find the Sanxingdui, have found lots of shale from Indian Ocean. So just the summary and the sum of the takeaway. The Sanxingdui challenges a traditional narrative of the integration of cultures in early China during major Bronze Age. And Sanxingdui reveals possible links with other ancient civilizations in West Asia. And the early globalization or the diffusion of technologies, the spreading of the stories, happened in way more larger scale, and way more larger scale on the old continent, and way earlier than we could ever imagine. So that's it. Thank you.
Very cool and very interesting talk, Lisong. Thank you so much. a Zoom round of applause for your great talk. Before I take the questions, I would just like to post the feedback form link here. Please take a couple minutes before you leave the Zoom room to like fill the form. It would be really helpful for the speakers for future as well to improve on their talk skills. But this was super informative. I have never heard of like any historic piece of information regarding this, so I was very intrigued. I hope everybody enjoyed it. I do see a couple of questions here if people are not raising hands in the Zoom room right now. So I'll just take those. First question is, weren't these masks too heavy to wear? Maybe made of rocks?
Yeah, that's a good question. So we believe that so there are lots of masks, and some masks like these, it could be some kind of mask used during the funeral, like when they put the people in the coffin, they will put a mask on, and they will probably use this. And some other crazy masks like the one I showed earlier, like this, it's probably for the ritual usage. And others like these, we have no idea what they were supposed to be used for, but we do see some kind of indications like the punch hole between their eyes. It must be some kind of object to hand them upon the air. So it's definitely not for people, but it's for the sacrificial ritual that we believe.
Gotcha, gotcha. I see Nick raising his hand. Please go ahead, unmute yourself and ask question.
Yeah, so is Jargon allowed in the questions or not at all? I guess I'm not just joking. So my question actually is, I've heard about another archaeological phenomena in China in the please correct me if I get any of this wrong, but the Xizang province, where there's the Tarim in the Taklamakan Desert in the Tarim Basin. There were a bunch of mummies found that a bunch of like different cultural markers on them and DNA studies kind of indicated that they looked like they'd immigrate or had migrated there from from the I guess the Central Eurasian steppe and the Central Asian region. Although of course that whole thing is a little controversial. Is there do you like, I don't know, do you have any thoughts on like whether these were connected in some way or probably separate? Or because I know you're kind of like, you're at the end, you're kind of drawing like a diffusive map moving your map of like cultural and mythological and technological diffusion kind of like eastwards from central or from like the Central Asian Near East sort of region. So do you see, I don't know, like, do you think that there's a connection to Tarim Basin or probably not?
I would definitely say they are connected, and they are Indo-Europeans. Indeed, I can tell you that for sure. That those mummies found in Xinjiang, Taklamakan Basin, actually they found lots of evidence, such as the literature. They wrote stuff on the wood, and because of the environment over there, it gets well protected, and those writing system turn out to be some kind of the ancient writing system developed from West Asia, and also the language that is carried by this writing system is called the Tocharian, which also turned out to be a Proto-Indo-European language. It's actually one kind of East Indo-Iranic language. It belongs to that branch. So which means the Proto-Indo-Europeans are definitely carry lots of things, including horse riding technique, the chariots technique, maybe the metallurgy, all the way from Black Sea to the Taklamakan Basin. But we don't know, the thing that we don't know is about the inhabitants. We don't know who were there in the first place. Just like the Sanxingdui, we believed people were there like 10,000 years BC for sure. But it's those people, those Indo-European who carried this technique. They brought all these high advanced technologies to them, and then merge with them in terms of culture and all that kind of stuff. So I think that's the picture out of it. I don't know if that gives you some kind of answer.
No, that was great. So, I mean, great talk.
Thank you.
Awesome. Amazing, Lisong. Thank you so much again for your for giving the talk today. I hope to see all of you again for the next new No Jargon Talk series next week. Please take time to give the feedback to the speakers. And yeah, we are already running a little late, so I would like to end the talk here. See you all next time.